Hello. Now that you've had a chance to work on linear inequalities and systems of inequalities and those kinds of things, I wanted to look at something specific, a specific application for these systems of inequalities called linear programming. Okay. Linear programming is used to find an optimum value. And that can be both either a maximum or a minimum. So you could have, might have to find minimum cost, or you might have to find maximum profit, or something like that. You're going to use the skills that you've learned with graphing systems of inequalities in this lesson in two variables. So you're going to be doing some graphing, you're going to be doing some shading, and then using the result to help you figure out a maximum or minimum if it exists. Okay, so the steps for linear programming, I'll go through some notes and then I'll do a couple of examples. You write all necessary constraints, which these will usually look like inequalities. And the objective function, which you'll use to test some of the values that you come up with and to find your maximum or minimum. Then you're going to graph what they call the region of feasible solutions. So when you graph your constraints, you're going to have you should end up with this region bordered with some edges and vertices. They call it the region of feasible solutions. And you identify all the vertices or corner points. You're going to test each vertex. Oh, I don't know why I said teach. I was thinking about teaching. Test each vertex in the objective function. And then the solution is the vertex producing the optimum value. And that's it. That's how you're going to use linear programming to find an optimum value. Okay, fundamental theorem of linear programming says if the optimal value for a linear programming problem exists, then it occurs at a vertex of the region of feasible solutions. This is kind of stating what we were talking about a little bit ago. You know, if you have an optimal value, once you graph the constraints and get your region of feasible solutions, if the optimal value actually exists, it'll occur at one of those vertices, one of those corner points. All right. So let's tackle a couple of examples. First example, we have a company that makes two products. They make video games and controllers. Each video game has a profit of $30. Controller, profit of $70. Must manufacture at least 10 video games, at least 10 games per day, but no more than 50 per day. Number of controllers cannot exceed 60 per day. Video games cannot exceed, number of video games cannot exceed number of controllers. Okay, we want to maximize daily profit. So when we do this, how many of each will accomplish this? And what is the max profit? Okay, so this is a situation where we're trying to find an optimal value, in this case a maximum profit. Now before I go to the next slide, I'm going to go ahead and take what I wrote here and talk about some of the things that I'm going to need. The objective function comes from the fact that each video game brings in a profit of $30 and each controller brings in a profit of $70. So I'm going to let X be the number of video games and I'm going to let Y be the number of controllers. My objective function will deal with profit. Since video games bring in $30, I'll do $30 times X number of games. And since controllers bring in $70, I'll do $70 times Y number of controllers. I'm going to use this profit function in a little later, towards the end of doing the work. Now the constraints are what's going to help me come up with my region of feasible solutions. When they say they must manufacture at least 10 games per day, but no more than 50 per day, I can express that as 10 is less than equal to X, less than equal to 50. X has to fall somewhere from the X, or the number of video games has to fall somewhere from 10 to 50. And when it says the number of controllers cannot exceed 60 per day, I can use that to write that 0 is less than equal to y less than equal to 60. The 0 seems obvious, but it's important to put it there so that you can, when you graph, you can get your vertices you need. You know, you can't make negative controllers. So in this case, they didn't say there was a minimum, so 0 would be it. But it can't exceed 60, so the number of controllers has to be under 60. It can equal 60, you just can't go past it. But also, number of video games cannot exceed the number of controllers. So the number of video games, X, has to be less than or equal to Y. The number of video games, X, has to be under or equal to Y. It can't go past Y. All right, we're going to use those 3 statements we came up with. We're going to use those 3 constraints. We're going to graph them all on the same grid and see what happens from there. And then once we get our vertices, plug them into that profit function. All right, so let me rewrite them up here. The profit function was $30 X plus $70 Y. And then we're dealing with 10 is less than equal to X less than equal to 50, 0 less than equal to Y less than equal to 60, and X less than or equal to Y. Okay, so I don't have graph paper with me today, so I'm going to do my best here to sketch this out. And I'm going to go by tens. Okay, if 10 is less than equal to X less than equal to 50, then I know that for my X values, they have to fall somewhere from 10 to 50. So they have to fall somewhere inside of this region here. And for 0 less than equal to Y less than equal to 60, I know those values have to fall somewhere in this region. You know what, let me draw the boundaries a different color so we can keep track of those as compared to the shaded area, basically. And then if Y is greater than or equal to X, Y equals X is a line. It looks like this. And then if Y is greater than or equal to that, then the shading for that is going to be above that line. Okay, so if we look at all the shading, we see that there's an overlap and a nice little polygon that exists in this area that I'm darkening. I'm going to try to exaggerate the vertices. So here we have our region of feasible solutions inside that polygon. Looking at all those overlaps where everything intersects each other. And we're ultimately interested in those vertices. Let's see, you have a vertex at 10, 10. So we're going to have to test that. You have a vertex at 50, 50. So we're going to have to test that. You have a vertex at 10, 60. So we're going to have to test that. And you have a vertex at 50, 60. So we're going to have to test that. Okay, so we're going to plug these into that little profit function up there, the objective function, the 30x plus 70y. So what we're saying basically is, like with 10, 10, we're looking at what's the profit when you manufacture 10 video games and 10 controllers. So when you do 30 times 10 plus 70 times 10, what do you end up with? You have what, 300 plus 700, which is $1,000. All right, something to keep in mind. 50, 50, 30 times 50 plus 70 times 50. So it was what, 1,500 plus 3,500? That ends up being $5,000. 10, 60, so that's 30 times 10 plus 70 times 60. So that's 300 plus 4,200. So that's $4,500. And then 50, 60 is 30 times 50 plus 60 and 70 together. So 1,500 plus 4,200, which equals $5,700. So we've plugged them all in, and then all you gotta do is look at which one's the most. Well, that 50, 60 turned out with the highest profit. So in order to maximize their profit, they want to manufacture 50 games and 60 controllers. And if they do that, the max profit is $5,700. And that's how linear programming is done. All right, let's do another example. A lady named Robin takes multivitamins each day. She wants at least 16 units of vitamin A, at least 5 units vitamin B1, and at least 20 units of vitamin C. Capsules cost 20 cents per capsules. So capsules cost 20 cents each. And chewables cost 10 cents each. Okay. Another thing about capsules, not only do they cost 20 cents each, but they contain 8 units of A, 1 of B1, and 2 of C. And then chewables contain 2 units of A, 1 of B1, and 7 of C. Okay, so how many of each should she take? To minimize cost, but still get the daily requirements. And what is the minimum cost? All right, we're going to let X be the number of capsules, and we're going to let Y be the number of chewables. Okay, so we can come up with a cost function, the objective function being about cost. We can say, oh, capsules are 20 cents each, times X number of capsules, plus chewables are 10 cents each, times Y number of chewables. So we're going to use that later when we're trying to determine that minimum cost and trying to determine which value gives us our minimum. Now for vitamin A, vitamin B1, and vitamin C, we can come up with our inequalities that we want to graph in order to get our region of feasible solutions. Well, for vitamin A, she needs, if she takes 1 capsule, she gets 8 units. If she takes 1 chewable, she gets 2 units. So 8 times the number of capsules plus 2 times the number of chewables, 8x plus 2y. And she needs that to come out to be 16 or higher. Because remember, she needed at least 16 units of vitamin A total. So she knows for every capsule, she'll get 8, and for every chewable, she'll get 2. So we can write a statement saying, well, 8x plus 2y has to be greater than or equal to 16. Then for vitamin B1, she gets 1 unit from a capsule, 1 unit from a chewable. So 1 times x plus 1 times y, and she needs that to be at least 5 units total when she decides how many capsules and chewables to take. Then for vitamin C, she can get 2 units from capsules, from each capsule, and she can get 7 units from each chewable, and she needs that to be at least 20 units, so greater than or equal to 20. And it kind of goes without saying, x has to be greater than or equal to 0, y has to be greater than or equal to 0, because you're not going to take negative number of vitamins in this case. All right, so we're going to go ahead and graph our inequalities there, find our vertices, and then use those in that cost statement there. Okay, so let me rewrite the inequalities we need to worry about. 8x plus 2y is greater than or equal to 16. X plus y is greater than or equal to 5. 2x plus 7y is greater than or equal to 20. It's going to go by ones this time. All right, if 8x plus 2y is greater than or equal to 16, we're going to have a y-intercept at 0, 8, and an x-intercept at 2, 0. So it's going to look like this. Then we know the shading's above that. So I'm not going to draw the shading right now, because I feel like it gets too cluttered. But just keep in mind that the shading's, you know, up, above, because the greater than or equal to. Then for x plus y greater than or equal to 5, we're at 5 here and at 5 here. And then let's see. It's going to intersect that one at 1, 4. Okay. I think that 1, 4 is going to be important. And then for 2x plus 7y greater than or equal to 20, that one, let's see here. I know it's going to go through 10, 0 down here. And let's see. Has a slope of -2/7. So I can go up to and over 7. And it'll intersect right there. And then it crosses the y-axis at 2 6/7, so almost at 3. So this is giving me a good idea of where it's all going. Okay. So that point is important at 3, 2. Because remember, everything's being shaded above. So if you really want to talk about the overlap of it all, the border of that overlap of all the shading goes to here, then goes to here, and then goes to here. And you got all this shading happening that's in common in that direction. This got this border down here, we got this border here, it just keeps going. All right, so we're focusing in on these vertices. So we have a vertex also at 0, 8, and we have a vertex at 10, 0. And we're going to go through and test what's happening with each of those vertices in our function. So we're going to take 8x plus 2y, or, no, sorry, not 8x plus 2y. We're going to take 20 cents x plus 10 cents y and test each of those in there and see which one minimizes the cost for her. So for 0, 8, if you plug that in, you get 80 cents. For 1, 4, if you plug that in, you get 60 cents. For 3, 2, if you plug that in, you get 80 cents. And for 10, 0, if you plug that in, you get $2. Okay, so the one that minimized it is right here. That's the lowest cost that it came out to. So she would expect to each day, she would take 1 capsule plus 4 chewables. And then that minimum cost ends up being 60 cents per day. If you look back at our data, it said she needed at least 16 units of vitamin A. Well, if you have 8 units and 2 units, you have 8 plus 8, which is 16. So you get your vitamin, she gets her vitamin A. She gets the minimum of that. She needed 5 units of vitamin B1. Well, there's 1 in each, so that would be 1 plus 4, which is 5. So she gets her minimum B1. And then for vitamin C, there's 2 units in each capsule, 7 units in each chewable, so she'd have 2 plus 28, which is 30. So she definitely would get her minimum, but she'd actually go beyond that. You know, she needed at least 20, she would get 30 units of vitamin C. So she gets her minimums, and she's also minimized the cost for that. And that was all with linear programming. All right. Thank you for joining me, and look forward to seeing you again soon. You know, eventually we're going to talk about matrices again.